I've joined. I've joined, sir. So you can make me a co-host. Hello, sir. Okay. Okay. Thank you, sir. Okay, I want to check the YouTube now, but I think it's working. Yeah, the YouTube is working, so we are good. You can send it to them. Thank you, sir. Wow, thank you so much. Okay, let me see. Hello, sir. Okay. So good morning, class. I think some students joined with that was the Zoom link initially given out. Please, can you call their attention to use this one? There was a link that was on before, but we decided to pull it down to use this. Please, can you talk to your friends that they should join with the new link that is sent to the Telegram? Not the previous one, because I have less than 100 students. The last time on Friday, I have more than 300 students in less than 5 minutes. So I think some students are still in that room. Please, can you tell your friends? Can you send this link to your friends so they can join with this link before we start? Thank you. POI 101 class is 8 to 9. So we are not waiting for anyone any longer. So good morning all. Welcome to today's class. I hope you guys you had a nice weekend. So we are going to start with the classwork that I told you, and then please just put down your name on the chat box as your attendant. So we'll be starting with the classwork. I just projected the question. The question says, predict whether the following compounds are ionic or molecular. Now, let me just explain some things to us. For an ionic compound is a compound that you actually have the cation and the anion coming together to form a compound. Remember the last class, we talked about cation, we talked about anion. We said that some atoms, they have the ability to lose the electron and they become positively charged. And this class of anions are referred to as cations. In other way, you also have species of atoms that have the capacity to gain electron and become negatively charged. They are called the anion. So when an anion and a cation combines together, they form ionic compound. We have a definition of compound the last class. Now, when you have two, let's say, two anions combining together, that two metals combining together, or, they give you what you call a molecular compound. They actually form the covalent bond. So I'm just giving you a clue to what you're supposed to know, a clue to guide you to the answer of this particular question. So please, can we go on to the chat box and predict if each of these four compounds are either ionic compound or molecular compound? Thank you. You could as well put down the answer after writing your name. You don't need to go to another space. Just your name, then the answers, please. We have lost about 17 minutes, so we have to be fast. Okay, you're taking it. Bamibola Taiwo Mary. I'm believing you're taking it according to A, B, C, D. That is your 1, 2, 3, 4. Because what is here is A, B, C, D. So I assume your A is 1 and that it goes that way. I want to see more answers, please. Abubakar. Only you. How many names? One person is okay now. Isaac, yes, it's covalent. It forms a covalent bond, but it's a covalent compound, yes. But what you're giving is molecular. So I always tell you guys that adhering to instruction is part of your examination. So because you're giving a specific word to use, please use molecular. We know it's covalent, but use molecular as specified in the question. Thank you so much. Which is ionic, which is molecular? Okay, sounds good. It's like, no, I think I've seen someone who did something that is not correct. So let me go to um okay. Temiolua, you said that lithium carbonate is molecular. Lithium carbonate. Remember the last class we looked at polyatomic ion, which somebody asked if you can call them radicals, and I say yes, they're actually radical. If you look at that, you find out that your carbonate, it's a polyatomic ion, is a radical. That means it has a negative charge. And lithium is a metal with a positive charge. So you have your cation and you have your radical, which stands as an anion. So that makes it ionic and not molecular. It makes it ionic and not molecular. So I think some of you are still struggling with this. So if we look at potassium iodide, potassium, it's a group 1 cation. It will lose 1 electron and become what? Positively charged. So there's a positive charge on potassium and there's a negative charge on your iodine. So when they combine together they form ionic compound because they are made from cation and anion. So that's what makes them ionic. They are ionic and not molecular. Some people are saying molecular, they are ionic and not molecular. Your peroxide is covalent. It is molecular because it is made from hydrogen, which is a non-metal, and again oxygen, which is a non-metal. So two non-metal species are combining together to form this compound. Hence, it's going to be covalent, and covalent is as well as calling them molecular compound. Now again, you come to the chloroform. The chloroform is composed of a carbon atom, hydrogen atom, and 3 chlorine atoms, all of which are what? They are all non-metals. And because they are all non-metals, they are going to form a covalent bond between them. This makes them molecular what? Compound. Now, lithium carbonate. Lithium will lose electron and become positively charged. This is a radical with a 2 negative charge on it. So the combination of 2 atoms of your lithium combining with one of this, because it has 2 negative charge, it's going to be lithium carbonate, and this is ionic because each of this species has a charge on it. So this is ionic, while A and D are ionic, while B and C are covalent. So we have to be faster. I think we have. So we stopped at atomicity the last class. You were able to make some, we were able to do some class work, and most of you got the correct answer. So we are moving to valency and oxidation numbers. Valency and oxidation number. Again, like I told you, the reason why we are taking all of this is for us to be able to write our chemical formula correctly. Knowing the valency of an atom, or the oxidation state of an atom in a molecule or in a compound, will help us to write the molecular formula correctly. And so, when we talk about valency, we are talking about, we are talking about the number of electrons present in the outermost shell. That is your valency. Now, these are electrons that are available for bonding. So it also determines how elements are grouped and all of that, and the maximum bonds they can form. In essence, it's just telling us that valence electron is actually what we use in bond formation. After this, we'll be looking at chemical reactions. Chemical reaction is all about bond breaking in the reactant and bond formation in the product side. So knowing the valency of a particular element will help us know how or what's the number of bonds that particular element will form with the combining element. Now, the oxidation state of an element is the number of electrons that element or that particular atom will lose or gain or share with another atom to form a compound. That is what oxidation state is all about. Now, usually we use signs like positive or negative symbols to write our oxidation number, the oxidation state of a compound. For example, here I have oxygen. The valency of oxygen is 6. That is, the number of the outermost electrons in oxygen is 6. Remember, oxygen is 1s2, 2s2, and 2p4. That is the second energy level. Energy level 2 has 2 electrons in the s orbital and 4 electrons in the p orbital. Combining them together gives us 6 electrons as the valency of oxygen. So oxygen has 6 electrons in its outermost shell. Now, the oxidation number of oxygen is what are the number of electrons that oxygen will gain or lose in order to be stable. Remember, I told us the last time that everything, whether living or non-living, will always want to be comfortable. So we always want a comfort zone. So even oxygen as it is, we want a stable state. And that stable state is what we normally refer to as the octet configuration. And so for oxygen to be octet, it needs to do what? To gain 2 electrons. Oxygen cannot lose electron because the amount of energy it will require to lose electron. So it's going to lose 4 electrons to be 2 if it wants to be 2. But it's easier to gain 2 electrons to be stable than to lose electron from the valence electrons. And so the oxidation number of oxygen is -2. This -2 is just showing us that oxygen will gain 2 electrons to be stable. That is to make its outermost electron 8 to form an octet configuration. So that is how you can get the valency. That's how to get the valency and the oxidation number of elements or atoms. Now, why do we need to talk about the valency and the oxidation numbers? I told us that it helps us to do what? In writing our chemical formulas, to know the number of atoms for any particular compound that it will share or it will give to another atom that is combining with. Now we are going to be looking at some examples here. What we want to do here is we want to combine this elements, chlorine, oxygen, and nitrogen with sodium, calcium, and aluminium. So we are going to be looking at the valency of each of them to know how to combine them. That is their combination ability. Now, we all know that chlorine will gain 1 electron to become octet, to have an octet configuration, that is to become stable. Oxygen will gain 2 electrons to become stable, and nitrogen will gain 3 electrons to become stable. And that is why you have their valency as -1, -2, and -3 respectively. In the same way, sodium will lose 1 electron to become a stable, +1. When it loses an electron, like we say, it's forming a cation and it's going to be what? A positive charge on it. Now, calcium will lose 2 electrons and aluminium will lose 3 electrons to be stable. That is to form a stable or to form an octet electronic configuration. Now, how does this elements combine with each other? Because sodium has a valency of +1 and chlorine has a valency of -1, they are going to combine in this ratio 1:1. +1 - 1 is going to give us 0. It's going to be neutral. All we want to form is to form a neutral compound. So it is the valency that actually tells you how the combination ability will be. If you look at sodium here, because sodium is 1 and oxygen is -2, now there's going to be a swap in order to maintain this neutrality of this compound. Sodium being 1 is going to take up two valency number of the oxygen atom, while oxygen atom will take that of the sodium. It's just like a swap. You're going to interchange their valence electron, the valence electron of the elements that are combining together to form the compound. Now, if you're using radicals or metals again, the same thing. This is ammonium. Ammonium has a +1 charge. This is hydroxide ion. It has a -1 charge. It's placed here. So when they combine in this ratio to form a compound. Same with sulfate. Sulfate has is a radical with 2 charges, 2 negative charges on it, and ammonium is a radical with a positive charge on it. So when they combine, there's going to be a change of the valency of that of ammonia to sulfate and that of sulfate to ammonium, and that is how you form your ammonium sulfate, and so on and so forth. So that is how you form your compound. So in writing your chemical formulas, you will need the knowledge of your valency and the oxidation numbers of each of the elements that are combining together to form a compound. Trying to. Okay, in summary, this is what we have been talking about. We have your magnesium. Magnesium is a group 2 element, and magnesium is to lose 2 electrons to become positively charged. We already know that nitrogen gains 3 electrons to become negatively charged. It's an anion, while your magnesium is a cation. So how do they combine? They combine in this way. The charge on the nitrogen is given to the magnesium, while the charge on the magnesium is given to the nitrogen to form your magnesium what? Nitride. In this way, the compound that is formed is electrically neutral. So it does not have any charge on it. So this is what you use to determine the formula of a compound. The charge on the cation becomes the subscript on the anion, and the charge on the anion becomes the subscript on the cation. So in this way, you form electrically neutral compound. Now, in a case where you have the subscripts, they are not in their lowest whole number ratio, you can always make them, you can always write them in their lowest whole number ratio by dividing with the greatest factor. There is an example here. The magnesium reacting with oxygen will give you magnesium oxide. If we follow what we've been saying before, that the charge on the cation becomes the subscript on the anion, and the charge on the anion becomes the subscript on the cation, you will note that magnesium will be 2 and oxygen will be 2. But if you look at this particular compound, they are not in their lowest whole number ratio, because a factor can have 2 dividing these two elements. If 2 divide magnesium and 2 divide oxygen, you have them as magnesium oxide, the way it appears. And this is how it is normally written, and not in this form. So when you have them in, when you don't have them in their lowest whole number ratio, you should always bring them in their lowest whole number ratio. And that is what we always learn when we talk about our empirical formula. So, you know, all these things is, I don't know, there's a way they overlap. This is just talking about what? The empirical formula. Now, this is where the application of what we have been saying is, this is where we are going to apply it now in our chemical equations and reactions. Now, when we talk about chemical reaction, we're actually talking about, you know, transforming a chemical substance into a new chemical by breaking bonds in the reactant side and making bonds in the product side. So bonds are breaking and bonds are made. In that way, a chemical reaction takes place. Now, how do we represent a chemical reaction? How does chemists represent a chemical reaction? Chemists represent a chemical reaction using what we call chemical equations. We use symbols of that substances in form of their equation to represent them, because our language is language of equation. Just like the English people, in this hydrogen, they will just write hydrogen as HYDROGN plus. But no, in chemistry, we understand the sign of symbols. So if we represent our equation this way, anybody that sees this will know that hydrogen is reacting with oxygen to form water. So you don't need to start writing hydrogen as in words. But there is something again about chemical equations. A chemical equation must be balanced. If you write a chemical equation that is not balanced in chemistry, you have given a false information. And that is very, very dangerous. You don't give a false information, because if I put 2 here, I am saying that 2 moles of hydrogen is reacting with 1 mole of oxygen to give me 1 mole of water. This is very, very impossible. If someone takes this to the lab and want to produce this 1 mole, it will take the person an eternity to produce it, because that is not what is obtainable. So what means is this: we need to look at the stoichiometry of the reaction. The stoichiometry of the reaction is very important, because that is what gives a balanced equation. When you write the correct stoichiometry, you get the what I mean is that looking at the amount of the reactants to the product in terms of their mole ratio, their mass ratio, their volume ratio, depending on the area you want to look at it. One may decide to look at the mole ratio. Somebody may decide to look at their volume or their mass ratio. But whatever ratio, whatever concept you want to use, we have to make sure that the chemical equation is balanced. And what do I mean by balancing a chemical equation? The number of what you have on the reactant side must be equal to the number of substances in the product side. In that way, you know that your chemical equation is balanced. So we'll be seeing examples as we go on. I don't know why this is becoming stiff today, and it's actually disturbing the class. So let's look at some types of chemical reactions. We'll be looking at the first is the combination reaction, or what we refer to as the synthesis reaction. Now, there's going to be a class work, I think not here. Where is that class work? I'm supposed to give you a class work. Okay, let's go on. Maybe I'll have to do it later. Now, in combination reaction, or what we refer to as the synthesis, sorry about that. What happened? Okay, the synthesis reaction. You have two elements or one element and one compound combining together to form a single product. Listen again. It could be that you have two elements, or you could have one element and one compound, or you could have two compounds combining together. But the thing about combination reaction is that your product is just one thing. It is single. Your product is one. I have an example here that A plus B will give you AB. You could see that I do not have plus C or plus B prime. Is A plus B to give me AB. So whatever that is, the species that is combining will give you a single product in what? In combination reaction. Some examples are here. Your potassium plus chlorine will give you potassium chloride. Then iron plus oxygen, you have your iron oxide. And if you look at all of these elements that combine, they are balanced. You see that the number of potassium on the reactant side is equal to the number of potassium in your product side. And so also the number of oxygen in the reactor side is equal to the number of oxygen in the product side. So that is very important. Because your exam is going to be, I think, multiple choice question, you have to be very, very careful when you're giving a question, because one can glance at this particular equation. Maybe, I don't know, maybe I will put magnesium plus oxygen to give magnesium oxide, and I might decide to put 2 here, I mean in the product side. Then I will not have 2 moles of magnesium oxide, and somebody will say, it's balanced because magnesium is 1 here, magnesium is 1 here, oxygen is 2 here, oxygen is 2 here. Remember, you should apply what? You should apply your knowledge of valency and what? And oxidation number first to know how the product will be. You know that you have 2 of these, 2 of these, and again you need to do what? To bring them in their lowest whole number ratio. So the knowledge of what we have done under valencies and oxidation number is very important in writing chemical equation or knowing a correct balanced chemical equation. Now you have these examples here. When you get the slide, please always look at them one after the other and make sure that you understand each of the equation and that you have the same number of elements as it appeared in the reactant side and the product side. Now, what also is important here is the state of the state of the elements or the compounds. Now, it's very important to note their states. Anyways, for now, I will say for combination, for these reactions, yes, it is important because the state, the state of the reactants and the product will actually tell you your net ionic equation. It will give you your net ionic equation. That is the actual species or the actual element that is undergoing the reaction, and give you the spectators ions. So it's very important. Even if we are not going to do it here, I'm not going to do it with you. I know that one lecturer will take care of that. So you know what your net ionic equations are, which particular species is undergoing the net ionic reaction, and which are the spectators ions in the equation. It's very simple, is what you can understand. So don't bother yourself. When the time comes, you will learn it. Now, the second type of reaction we want to look at is the decomposition reaction. As the name goes, decomposition, breaking up, splitting, to decompose, you know, you're breaking something into simpler what? Into simpler forms. So what this is telling us is this: it is the opposite of what? Combination reaction. Remember, in combination reaction, we have two things combining to give us a single thing. Now, in the decomposition reaction, what we have now is a single entity breaking up to give us two products. You see, AB is giving us A plus B. So once you get this right, you will be able to always know which, to always know the type of reaction for any particular balanced equation, in case if you're asked to name the type of reaction that is going on. Now let's look at what happens in decomposition reaction. Because in decomposition reaction, you need to break something, you need to split something, so you need energy to do this. So it requires an input of energy. So you need energy, and you know that in reactions, energy could be in form of heat, it could be in form of light, or it could be in form of electricity. So there's input of energy in decomposition reaction against your combination reaction, where energy is not required for the two reactants to come together. Now we have some examples of our decomposition reaction here. The first is hydrogen carbonate. Again, your knowledge on valency, your knowledge on oxidation number, your knowledge about your radicals, about your cations and anions, you apply it here. Remember that you have hydrogen carbonate, which means that you have this as a positive species. And remember that your carbonate, what? Your carbonate is a radical having what? 2 minus. So you actually know that this is where whatever that is happening here. So this particular equation, when you break it down, it's going to give you water and carbon 4 oxide. Your sodium hydroxide will give you sodium oxide and water, and so on and so forth. You can as well look at the other equations that we have here. And also you should note that it's always AB giving you A plus B, AB giving you A plus B, AB giving you A plus B. Now the next type of reaction is what we refer to as displacement reaction. Displacement reaction is, you also have double displacement. In this way, we are describing single displacement reaction here. Displacement, meaning that something is taking over the position of another. Now there are rules guiding this. Before I say the definition, there are rules guiding displacement reaction. There's what we call the reactivity series of metals. Some metals are more reactive than the other and will take their position during a reaction. What do I mean? Let's first of all define what a displacement reaction is. It's replaced by another reactant. Now, part of one reactant is replaced by another reactant. If you look at displacement reaction, you always have AB and you have a C, which means that you have a single element as a reactant, then you have a combination of elements as another reactant. So you have two reactants, one is a single element, the other is a combination of 2 plus copper sulfate. Now it says one part of the reactant. So if you look at it, reactant that can be replaced here is where you have your copper sulfate, because your ion is just ion, so there is nothing there. So it's either something is replacing something here. Is it copper that ion is replacing, or is it sulfate that ion is replacing? Now, for you to note this again, you should, the knowledge of your valency, oxidation number, cation and anion is applied, because definitely we know that iron is metal, so it's positively charged, and here copper is positively charged. Your sulfate is a radical with a negative charge, and for you to have electrically neutral compound, it's a combination of positive and negative, so iron cannot be displacing copper. I don't know if you're getting me. Iron cannot be displacing copper. So what happens is this: your iron is going to be displacing the sulfate in copper. So you have iron sulfate, iron sulfate plus copper. And now, why is it that iron is actually displacing copper in the here? If you look at this reactivity series, you see where iron is. This is iron, and reactivity goes down this way, so which means that potassium is the most reactive, followed by sodium, followed by calcium, followed by magnesium, telling us that iron is more reactive than copper. So iron will always displace whatever anion that is attached to copper in any chemical reaction, meaning that copper cannot displace iron in a chemical reaction. Now and again, let's go to the fifth, 1, 2, 3, 4, 5, to the fifth reaction here. You have magnesium and you have copper sulfate. Now, looking at this series again, magnesium is more reactive than copper, and so magnesium will displace copper in this place. This is the reactant side, so magnesium will take the part of copper. So what you have here is magnesium sulfate, and you have copper as what? As a metal here. Now and again, zinc again, because zinc is more reactive than copper. That is why zinc will displace copper in this reaction. Now I'm going to ask you a question. Though it is not written, but can you write it on the chat box? I want you to write zinc sulfate plus copper, ZnSO4 plus copper, and tell me what the product will be. Zinc sulfate plus copper, the reaction of zinc sulfate plus copper. I'm going to the chat box now. There is something I want to establish. Let's go to the chat box. Sorry. Zinc sulfate plus correct. Good. I see a lot of people. I'm so happy that you guys are understanding it. Exactly what I want to see. I give it up to you guys. I give it up to you guys. You guys are good. You guys are good. You guys are good. Now, I want you to tell me the reason why whatever you said won't happen. Give me the reason. Please, if you don't understand what we are doing, just put it on the chat box that I don't understand. Because everybody has to follow the class. We all paid our school fees and we are here to understand the class. So please do not follow the trend of the class. When everybody is saying, this, you now say, you carry on, this is what they are writing, let me write. If you don't understand it, let me see. Okay, I'm seeing some people I don't understand. No problem, I'm going to explain it to you. But I am happy that a lot of us are really understanding the class. Good, good, good. I give it up to you. Guys are good. You guys are good. So let's, for the interest of those that don't understand it, okay, Esther, you're raising your hand. Let me see if I can unmute you. Esther, can you, is it possible to unmute yourself and let me have your question? Esther, can you put the question on the chat box? Okay, let's go to this again. Some people say they don't understand. Now, I said instead of having copper sulfate plus zinc, I want us to have zinc sulfate plus copper. And a lot of you got the answer. Yes, it is not feasible. It will not react. And let me explain why it will not react. Now, it will not react because let's look at this series, this reactivity series of metal. This is zinc here, and this is copper here. What this is telling us is that zinc is more reactive than copper. So if I have zinc sulfate and copper, copper is here. Copper cannot replace anything attached to zinc. Copper cannot replace zinc. Copper cannot take the position of zinc by forming a copper sulfate. No, it's not possible because zinc is more reactive than copper. So any of these elements that are more reactive than the other, and you want the lower reactive, the least reactive element to take part of that, it is not possible. You say that the reaction is not feasible, or that the reaction cannot happen. It cannot happen because zinc is more reactive than copper, and so zinc cannot displace copper in the reaction of zinc sulfate plus copper. So that reaction is not feasible. So you cannot have anything as a product. So can I go to the chart now? I want to see your reaction. Do you understand it now? For those of you that did not understand it before. Can I see your reaction? Do you understand it now? Please, yes or no, so that we'll go on. Okay, thank you so much, Esther. Okay, thank you so much. Thank you so much. So we go on. The next is double displacement. We have to finish chemical reactions because next week we are going to story about the atomic development of atomic structure. So I want us to finish. Sorry, my system is. I want us to finish the chemical. So let's go to the next one, which is double displacement. Now, in double displacement, just like we looked at displacement reaction, one part of a reactant replaces the other. Now, you should also note that an element that is more reactive than the other will not be replaced. For example, copper cannot replace zinc in a chemical reaction because zinc is more reactive than copper. So you look at that series, that reactivity series that I showed you now is very important. Again, remember, always bring the knowledge of your valency, the knowledge of your oxidation number, what your cation is, what your anion is, and the radicals you have. These are the things we have done, and these are the things you are going to combine in writing your chemical formula and in writing your chemical equation. Now, we want to look at double displacement. In double displacement, now, I want somebody, just go to the chat box. Can you tell me the difference between double displacement and single displacement? There's something I said about single displacement. When I mean single displacement, sorry, I'm just talking about displacement reaction. I'm talking about displacement reaction. There's something about displacement reaction that I said when I was taking that slide. So can you tell me the difference? What did you notice about the double displacement and single displacement? Now I'm going to the chat box. We have to be fast because our time is running. Did you notice anything? Yes, ma. I want you to tell me. No, you still have your non-metals, their reactivity in they have their own reactivity. I'm going to show it to you. It's not only metals. We are just taking metals because of the reactions that we have on the slide. So that is why I put up that one so that you can understand it. When it comes to, swapping or each of the radicals that will take its position, like fluorine is very, very reactive. So when you have a fluorine and a chloride, you know that your chlorine will never displace fluorine because fluorine is more reactive than chlorine. So we are going to look at that, but a step at a time. Can you tell me what you noticed about only one reactant is replaced? No, let's just look at the reactant side. You know, in single displacement, what we have is AB plus C. AB plus C. AB plus C. I just want you to see it in that angle. That will make it easier for you to understand. Exactly. Correct. There is no ID element. There is no ID element. You have what you have is compound. You have species of cation and anions combining for both reactants. So you have ABCD. That is what it means. Good. That is exactly what I want to see. Now let's go to double displacement. Quickly, we are going to be fast about this. Like we said here, what you exchange here is you exchange the ions of each. So listen to me now. Remember that each of the reactants, you have two reactants. Each reactant has cation anion. The other reactant will have cation anion. So in double displacement, let's say that reactant A has cation A, anion A. Then reactant B has cation B, anion B. In double displacement, cation A will go with anion B, and cation B will go with anion A. That is what double displacement is all about. Let's look at an example here. You have your silver nitrate and reacting with your sodium chloride. Now, your silver is the cation here. The nitrate is the radical, which is the anion. In sodium chloride, the sodium is your cation. The chloride is the anion. So what it means is that silver of nitrate will take the chloride of sodium, and sodium will take the nitrate of silver. So you have sodium chloride and silver nitrate. So it's just the exchange between two of the reactants to form a new product. So in what happens is that the cations and the anions in the two reactants, they switch patterns to form products. It's just like trade by pattern. Give me your own, I give you my own. Give me your cation, I'll give you my cation. Give me your anion, I'll give you my anion. That is what it means. You see why I said it's very important you understand the cations, the anions, you understand your radicals, and you understand their valency and their oxidation numbers. Because without that, you won't be able to write a chemical equation well, and you will not be able to balance a chemical equation. So, to the chart now, should we continue? Yes or no? Quickly, we have 2 minutes. Can round up in 2 minutes. Though we didn't start on time. Any question? Or you want me to go on? Any question? Any question? Good. 2 compound swaps. Exactly. Excellent. 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 You guys are doing well. You guys are good. So, should we continue? I'm not seeing any reaction about continuing the class. Okay. So let's just round up with this. Oh, sorry about that. Now, the next type of chemical reaction is the precipitation reaction. It's just the formation of an insoluble salt when you have two solutions combining together. So when you have a reaction in which an insoluble salt is not formed, that reaction can never be a precipitation reaction. In a precipitation reaction, you must have an insoluble compound. That is, you must have solids that are formed as your product. Now, which means that solubility rules is being applied to determine if your product is soluble or not. Now, why do we need to apply, just as we applied the reactivity rule for metals to know which metal displaces the other, we need to apply this rule to help us determine if a particular element is present in the solution, or if that element is present, if it's present in the solution, so that maybe you do one or two things to precipitate it out. Because sometimes the products will be, the products will be in the solution. All you need to do is to just maybe allow some of the solvents to escape, reduce the quantity of your solution to precipitate out whatever you have there. So you need that particular rule to guide you to know if your salt is soluble or not. Now, I'm going to leave us with these rules. Just go through them. It's not difficult anyways. It is not difficult, but if you have any issue with them, we can come up with them the next class. I actually want to finish this class today. I want to finish this class today, honestly speaking, so I could start the the modern theory of atomic structure. Or what do you say? You want us to go over it? Yes or no? Is this something that you can do? You know, I trust you guys now. Is this something that you can do? Okay, instead of wasting our time, let's look at it together. Now, in precipitation reaction, you have both reactants as aqueous and you have your product as solid. That is what we have said, that your solid must, your product must be in solid form, or it must have an insoluble salt. Now, the rule is this. When you form a salt with group 1 cations, you know group 1 cations, your potassium, your sodium, and all of that. But there is an exception to group 1 salt, which is your lithium. When you form a group 1 cation salt, or you form with ammonium salt, you have any salt that you form, they are soluble. I said the exception to this rule is salts of lithium. So salts of sodium, salts of potassium are soluble. That is what it's telling us. Now, when you have your acetate, remember your radicals or your nitrates or your perchlorates, they are all soluble. Now you have your bromides, your chlorides, your iodides, they are soluble. Sulfates are soluble, but you have exceptions. When you have your calcium sulfate, your barium sulfates, they are insoluble. So what this means is this. You're just looking at the product side. When you form the product and you have calcium sulfate is not soluble. That means that you're going to form a precipitation. It undergoes a precipitation reaction because you have an insoluble salt. Barium sulfate as a product is what is insoluble. So it's going to undergo what we call precipitation reaction because it is forming an insoluble salt. That is what all these rules is telling us. Now, let's look at example here. You have sodium hydroxide plus magnesium chloride will give you sodium chloride plus magnesium hydroxide. Now, if you look at your sodium chloride is aqueous. The magnesium hydroxide is actually your precipitate. The magnesium hydroxide is actually your precipitate, and that is what you're going to use if you're to write the next chemical equation. It is what happens to give you the magnesium hydroxide that forms your net ionic equation. All of this one, your sodium hydroxide and all sodium chloride, they are what we call spectators what? Ions. Maybe I'm going to make another slide. It's not here. Maybe the next class I will make another slide to explain this better, because the way it is here, it is not clear, so that you understand what I mean by net ionic equation and general equation. What is given here, this first equation is referred to as general equation. When you want to consider the net ionic equation, you're actually looking at a unique equation or a unique reaction in that particular equation, and that is the one that gives you your solid or the insoluble salt. In this case, it is magnesium hydroxide. Now, to end the class, like I said, if all the ions in the reaction are shown to be soluble, then that reaction must not be a precipitation reaction. It can only have a precipitation reaction when your product or one of the products forms an insoluble salt or is insoluble. Now, quickly, let's wrap up with exothermic and the endothermic reaction. Sorry, I want to see the number that is here. Oh, sorry about that. Okay, let me see what you're doing. Your hands are raised. Oh, I don't have. Maybe I will get one for you. I don't have a mimic, but I can actually deduce one. I can actually deduce one. By the next class, maybe we'll share it. But you two, you guys are Gen Zs now. You can get one and let's look at it together, you know. So it's maybe it will go by your name. My slides aren't showing. Ah, you only see my face. Wait, let me share the slides again. Sorry about that. So, so this is where we were, and I think it's going to be the end of class. So I won't do what the biology lecturer did, taking up another person's class. So the next class, we start with the exothermic and the endothermic reaction, and we are going to actually introduce the modern atomic theory. You're seeing the slides now. Sorry about that. I didn't know the slide wasn't showing. Now I'm going to send the slide. Yeah, I am going to do that, but not now. It's when I'm done with the class, I am going to send it to you. So sorry about not seeing the slides, but you can hear me now. So, oh, how do you differentiate a soluble salt and insoluble salt? Like following following that solubility rules, you can see that there are some salts that you know that are insoluble, like calcium sulfate is an insoluble salt. Just follow the rules. You will see that they will tell you that the lithium group 1 salts are soluble except lithium. So any lithium salt is insoluble. Every other group 1 salt, sodium chloride, they are soluble. That's why I say just look at the rule. It's not that you cram it. I don't know how to do it, but when you memorize or you go over the rule over and over, you get to know the ones that are insoluble and the ones that are not soluble. Now, when you're writing an equation, or when you see an equation that they wrote AQ underneath it, that means that it is soluble. Now, when you see equation that in brackets they put S, that means that it's in solid form. You understand me? If they put I, that means that that particular product is in liquid form, or it's something that you can isolate at the end of the day. So that is how you can know it. There is no rule to knowing what is, which is soluble and which is not soluble. It's just following that rule that is there. I have not talked about the endothermic reaction. I said we are going to start with the endothermic reaction in our next class, and that is on Friday. So is there any question? Any question, please? How do you get the slides? The way you got your link is the way you're going to get the slide. But I don't give students slides till I finish the class. When I finish this chemical reaction on Friday, I think I'm going to give you your slide, your first slide on Friday to cover up what we have done. Then the atomic theory is going to be after the atomic theory that I'll give you that slide. Wait. Sadiq, maybe I don't know how we'll do it. Can you meet me? My office is room 230, the foundation building. If you know Faculty of Science, the building behind the Faculty of Science is called the Foundation Building. My office is room 230. You can meet me. I will explain. Because my time is over and I have another class now at 10. So I can go for my other class. Is that okay? Thank you. Akintola, you can meet me too. Okay, thank you, everyone, and do have a nice day. See you on Friday. Thank you too. Thank you too. Thank you too. Thank you, thank you, thank you. We are, to me too, I love you guys. But be good and read your books. Remember, the next class, we are going to start with our class activity. So you guys should get ready for me. You can come anytime you can. I'm available for you. But don't come on Tuesdays, though. You can come today or you can come on Wednesday, Thursday. I am here. Now, please remember our rules. Starting the class with class activity. Then, before we go on to the next, I said 230, not 203. Thank you.